Hello, everybody. Today I will be presenting some work I've been doing with some colleagues, Sofia Brander from BFS and Ole Ross from BGR. And I'm gonna, explain, this is the clicker, yes, thank you. I'm gonna talk about a radio xenon event that we saw over Sweden in the Swedish cube array, but also in several IMS stations in November and December 2022. And this was a fairly anomalous event. It was a sum of the highest radio xenon levels ever measured in the cube array, in the Swedish array. And the aim of this work was to firstly identify the source and understand the source term for understanding the radio xenon background in Europe, which is very important for CTBT purposes. But this was also an excellent opportunity for us to compare what a cube array, so array of Sana cubes, could accomplish when compared to the IMS system. Just to start introducing the data, this is what the situation looked like at the time in Sweden. So what you see on the map to your left is kind of the setup of the radio xenon systems in Sweden in November and December 2022. So the green scatter points are the cubes, so which were a part of this, what we call the Swedish cube array. And then we also have an IMS station in Stockholm, Ch3, which is yellow scatter points. And this is the observations of radio of xenon 133 during this time period for the 4 different cube stations. And please note that the y-axis differs between the different plots, but most interesting maybe is cube 3, which had a very large peak of 100 millibecquerel, and also cube 4, which had 2 large peaks of 50 millibecquerel, which is very unusual, some of the highest levels we've ever measured. So this was a very large radio xenon release. And this is the situation at the same time period for the IMS stations. So what we have here are measurements from 9 IMS radio xenon stations, which detected CTBTO categorized sea level during this time. And we believe from this work that this radio xenon detected in SCX63, so Stockholm, and also the Norwegian station, NOX49. So the gray and the pink lines here are definitely from this event, but we also suspect that this event was seen in Germany, in Canada, in Japan, and in Mongolia. So what we did when we started to investigate this event was we did some initial investigation where we looked at backwards atmospheric transport models from all of these samples. So this is a snapshot of one of these samples. This is a snapshot of an ATM model, 48 hours from the time the sample was collected. The sample in question is the one indicated by the green arrow. So this means that 48 hours before we collected this sample of radio xenon, this colored area is where the air was. So we did this for all of these samples where we found radio xenon, and this is just an example of 6 such samples. And maybe you can see a trend here. It seemed like all of these samples contained air that arrived from a very similar part, so for east of Sweden. So from this initial investigation, we draw some initial conclusions about kind of like what we would think the source were from. So all the SRS fields indicated that the air from all of these samples during all of this 3-week period came from approximately the same direction. It was east of Sweden. This must have been a really large release, otherwise we wouldn't have seen such high levels, so 100 millibecquerels, it's very, very large. This must have been possibly been an extended release, so something that was continuously releasing radioxenon for days or even weeks. And a final conclusion was that it's very probable or possible or even probable that this was just one source because of how the backwards ATM looked like. To further investigate this, we then did a forward ATM investigation where we had, basically we constructed a grid setup where we had several grid points spread over Middle and Eastern Europe where we suspected the source was from. And for each of these grid points, we ran one forward model per day with 24 hours release. We then varied the level of the source term for each of these day models to best fit the observation, and then added them to compare with the observations. And basically, for this scheme, we fitted each of these grid points with the observations for all of the 4 cubes. So there's a lot of observations from different places that would fit it with each grid point. And this is we used a cost term, if anybody's interested about that looked like this, with the Tikhanov regularization. And once we found our best guess for each of these grid points, we can then compare how well can that grid point predict the measurements. And from this, we can give a score to each of the grid points and find the area that is most likely to contain the source site. So this is what such a result looks like. What is shown on this is a map. The colors represent the Spearman correlation between the grid points and the cube array observations. And then the red area is where we get the best correlation between the models and the observations. Green, a little bit like medium correlation. Blue, lower correlation. And then where there's no colors, basically no correlation. And just to show kind of like what the result of one of these investigations looks like, this is a fit to a site that we know, so a nuclear power plant, in this red area. So this is the Kursk nuclear power plant. And what you see to your left is the observations in the solid lines, solid colored lines. And then the striped black lines is the model fit using Kursk as a source site. And just initial conclusions about this is that, for example, if you use Kursk as a source site, you can fit the observations very well. We basically fit all of the features except this first peak of cube 4 very, very well. So this is a good candidate for potential source. To your right is the source term that would be needed to produce the observations using Kursk. And these are in becquerels per day over the relevant time period. And they are fairly large, between 10 to the power 13 and 10 to the power 14 becquerel of xenon-133 per day that would need to be released. All right, so on to the maybe second interesting thing that we did with this is that we have the cube array, and then we also had the IMS station. So what we could do is we could do exactly the same procedure, but instead of fitting it to all of the cube array, so the 4 stations in the cube array, we only fitted to the SEX63, so the IMS station observations. So to your left is what you saw before, so the cube array. to your right is the IMS station. And there are basically two very interesting things that happens when you use more stations. Even though the SCX63 station is a more sensitive station, with 6 hours collection time to compare to the 12-hour collection time, using the array, you do shrink this area of very high correlation by about, I think about 75%. So that's the first thing. So you get a smaller area of very high correlation. And the second thing is, you see this high correlation around Stockholm, which is also where the station is located. When you use a grid approach like this, and you only fit to one station, you will always find a perfect solution for a local source. But when you use the grid, you remove this, this probability of a local source. Yeah, so just to conclude, we saw a very large xenon release in November, December 2022. This was seen in both the IMS in the Swedish cube array. And this was, for us, interesting in two ways. Firstly, to understand kind of like what type of levels of xenon do we see in just the background. And this was very much for a CTBTO context. But this was could also be used to showcase the strength of using an array of measurement, so a denser array than the IMS of xenon measurement stations compared to a single IMS station when trying to localize an event. And also we needed a quite high source term to fit these observations, about 10 to 13 becquerel or a little bit more per day. Thank you.
Thank you very much, Sophie, for your presentation. Are there any questions for Sophie? Yes, Suzanne?
Hi, Sophie. That was a really interesting presentation. I noted at the beginning you mentioned that you thought the signal had also been seen on several other IMS stations.
Yes.
And I wondered if you had plans to extend your forward modelling and cost function and to estimate the source to those IMS stations, and whether you felt that the added background that those stations might see might complicate that inversion, or whether it would add to what you've already seen.
Okay, so for your first question, I'm going to advertise a paper which is being written about this, where I've done this. So this has been done. It hits the station. It looks consistent, I would say. For the second part is, these stations are so far away. So we are talking about traveling maybe a week or 2 weeks almost, or like 10 days. And by that time, if you do any backwards modeling, your area is huge. So it doesn't really constrict the area very much. The Norwegian station, NOx 49, for sure could be used in an inversion. But the other ones don't really add a lot of information, because by that time, the xenon has spread so far.
Thank you.
Yeah.
Thank you. Yes.
Oh, well, thank you for this very interesting presentation. I might have missed it, but you mentioned in one of the last slides that you used the IMS station solely without adding it to the Kuber measurement stations. Does it improve when you add them together?
No, not very much actually. This has also been done. The area is very similar when you use 5 stations compared to the only 4 cube stations. So we interpreted this as it's being very important that you sample. So basically what you do is when you have a lot of these cubes, is that you sample simultaneously larger part of the plume, and we interpret it as this is the important feature that you add.
Okay, thank you very much, Sophie. We need to move on to our next speaker. Unfortunately, Matt